Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wondered why psychologists need to carefully plan the order of things they show people in experiments, and why just mixing it up randomly might not be enough? Well, this new tool, Shuffle Go, is trying to solve that exact problem for researchers. Scroll Shuffle. A tool for generating quasi-randomized stimulus lists with sequential constraints to scroll. So imagine you are running a psychology experiment. You've got a bunch of pictures or sounds, things you want to show to people to see how they react. You want to mix them up so that one person doesn't see them in the exact same order as another. That sounds simple enough, right? You could just hit a shuffle button. But here's the tricky part that this paper talks about. Sometimes a totally random mix can lead to weird patterns that mess up the experiment. Scroll-long runs of trials belonging to the same stimulus category, or target items appearing too close together. Think about it. What if, just by chance, someone sees 10 pictures of dogs in a row? Or what if, in an experiment looking at how quickly people respond to important versus unimportant things? All the important things just happen to appear at the very end of the list for some people, and at the beginning for others. These kind of super long streaks or unusual groupings can actually change how people behave or respond. Not because of the thing you are testing, but because of the order itself. This is called a sequential effect, and it can totally confuse the results. The practical solution is quasi-randomization, generating permutations that are random in a global sense, while obeying local sequential constraints. That is where this new tool, called Shuffle Go, comes in. It is like a super smart shuffle button. It doesn't just mix things up randomly, it mixes them up in a way that still feels pretty random overall, but it makes sure to avoid those really awkward streaks or patterns. Researchers can tell it specific rules. Like, don't show the same type of thing more than twice in a row, or make sure that if you show an important item, there are at least 5 other items in between before you show another important one. Two types of constraint can be imposed on any column, a maximum. Repetition constraint limits the number of consecutive rows that may share the same label, and the minimum gap constraint requires a minimum number of intervening rows between any 2 rows sharing the same label. The paper explains there are 2 main ways it does this. One is called the constructive algorithm. It basically builds the list step by step. It starts mixing things up, but if it sees a potential problem brewing, like putting the same thing in twice when it should only do it once, it stops and finds a different item to put there instead. It is like building a perfectly balanced Jenga tower. It is fast and usually works great for most experiments. The other method is called the equiprobable algorithm. This one is a bit more of a purist. It basically generates loads and loads of random lists, and for each one, it checks if it follows all the rules. If a list breaks a rule, it throws it away and tries again. It keeps doing this until it finds a list that follows all the rules and is also equally likely to be picked as any other valid list. The equiprobable algorithm draws random permutations repeatedly until one satisfies the constraints, guaranteeing an unbiased sample from the set of valid permutations. It is slower but preferable when distributional properties of the randomization matter. This second method is slower, but it is really important if the exact statistical pattern of the randomization matters for the analysis. Think about it like this. The constructive method is like a skilled artist making a beautiful painting quickly. The equiprobable method is like a librarian meticulously organizing every single book on a shelf so that every possible tidy arrangement has an equal chance of being the final one. The simplest correct approach to constrained shuffling is rejection sampling Jenner, a uniformly random permutation of the input rows. Check whether all constraints are satisfied, and if not, discard it and try again. The researchers developed this tool because, while other tools exist, they often have limitations. Some only work on certain computers, some are not open source, meaning anyone can see and improve the code, and some don't offer this special equiprobable mode. This new tool, Shuffle Go, is designed to be super accessible. ScrollMix is widely used and well validated, but is limited to Windows, is distributed as a closed source binary, and provides no command line interface or embeddable library. It does not offer an equiprobable shuffling mode. It is written in a programming language called Go, which makes it really fast and allows it to be packaged as a single file that you can run on Windows, Mac, or Linux without needing to install anything else. That is a huge deal for busy researchers. Shuffle Go was designed to address these limitations while maintaining full compatibility with the same constraint model. And it is not just for super techie people. It has a command line interface for those who like to automate things, but it also has 2 nice graphical interfaces like little desktop apps that make it easy for anyone to use. Plus, if you are a programmer yourself, you can even use it as a library within your own code, in either Go or Python. Scroll.it offers a command line interface, two graphical desktop interfaces. An embeddable Go library and a Python library. Scroll the input is simple. Just a text file like a spreadsheet, where each line is a trial, and different columns describe what is happening in that trial. For example, you might have columns for the image shown, the response the participant should give, or the condition they are in. Scroll input is a plain text or CSV table whose rows represent trials and whose columns represent categorical variables, e.g. stimulus type, response mapping, condition. Scroll then, you tell Shuffle, go your rules. For example, if you have a column for stimulus category, you could say max 2 to mean no more than 2 of the same category in a row. Or if you have a column for target item, you could say 10 to mean a target item must have at least 10 other items between it and the next target item. Scroll, for example, given a stimulus list with 3-column stimulus identity. Category, word or pseudo, and frequency band, high or low the constraint string. 0 to 1 imposes no constraint on the first column, allows at most 2 consecutive rows with the same category, and allows no 2 consecutive rows with the same frequency band. Scroll the developers have a long history with this kind of tool going back to the late 90s. This Go version is the latest evolution, aiming to be the most accessible and powerful yet. So, what does this mean for us? Well, it means that psychological experiments are going to be designed more carefully. This leads to more reliable results, which means we can trust the findings about human behavior, memory, attention, and all sorts of fascinating things about the mind more. When studies have better randomization, we can be more confident that the effects we see are real and not just a fluke of how the trials were ordered. It also means that researchers can spend less time wrestling with complicated software and more time actually doing science. The fact that it is cross-platform and doesn't need installations is a huge win for making sophisticated experimental design accessible to more people, not just those in well-funded labs with expert support. Scroll Shuffle. Go was created by translating the Python library into Go in early 2026 with the assistance of Claude Sonnet and Anthropic. Scroll now, no study is perfect, right? This paper doesn't present an experiment with human participants, it is presenting a tool. The main finding here is that the tool works and addresses limitations in previous similar tools. The limitations of the tool itself, as discussed, are mainly centered around the speed of the equiprobable algorithm when constraints are very tight. If the rules are too strict, the equiprobable algorithm might take a very, very long time to find a valid list, or might not find one at all within a set time limit. Scroll, the main limitation of the equiprobable algorithm is efficiency. When constraints are tight relative to the structure of the data, for example, when half the rows share a label and the maximum, repetition constraint is 1 valid permutations are rare, and the rejection rate is very high. Scroll. But for the vast majority of experimental designs, the constructive algorithm is fast and reliable, and the equiprobable algorithm, while slow in extreme cases, offers that crucial guarantee of statistical fairness when it is absolutely needed. The real strength of this work is in its accessibility and utility. By providing this tool as free, open-source software that runs everywhere without fuss, the authors are empowering researchers to conduct better, more robust experiments. It is a behind-the-scenes innovation, but it is one that can have a ripple effect through psychology by improving the quality of the research that comes out. What is really cool is that this tool has a history, evolving from older programming languages to this modern, super efficient Go version. It shows a dedication to making this essential part of experimental design as seamless as possible. So, what is next? We can probably expect to see many more well-designed experiments using Shuffle Go in the coming years. Future research might involve even more complex constraints that this tool could be adapted to handle, or further optimizations of the algorithms. But for now, this is a significant step forward for experimental psychology, making quasi-randomization more powerful and easier to use than ever before. What do you guys think about the importance of carefully ordered stimuli in experiments? Let me know in the comments below. If you found this breakdown helpful, please give it a thumbs up, subscribe to RUBIN'S Mind Lab for more dives into fascinating research, and hit that notification bell so you don't miss our next video. Thanks for watching, and I'll see you in the next one.